Hello students, today's topic is types of non-ideal solutions. Solutions which do not obey Ross's law at all concentrations are called non-ideal solutions. That means some type of solutions, they will deviate from Ross's law. Then what is the meaning of deviation? Suppose if you take ideal solution, okay, consider a ideal solution of two components A and B. Then, according to Ross, vapor pressure of the solution is equal to sum of the partial vapor pressure of the components in the solution. That is, in terms we can write PA naught into xi A plus PB naught into xi B. Okay, solutions which obey these expressions, they are called ideal solutions. Then in case of non-ideal solutions, P total is equal to PA plus PB, that is not equal to PA naught into xi A plus PB naught into xi B. This is the meaning of deviation. This one is vapor pressure of the solution calculated by using Ross's law. Then this one is experimentally calculated value of vapor pressure of the solution. Clearly we can say vapor pressure of the solution is not equal to vapor pressure of the solution that is calculated by using Ross's law. Okay? So not equal means what? Either that is greater than the vapor pressure of the solution calculated by Ross's law, or vapor pressure of the solution is smaller than that calculated by Ross's law. Okay? So we can write vapor pressure of the solution that is equal to PA plus PB, either that is greater than PA into PA naught into xi A plus PB naught into xi B. This is one condition. Or second condition, we can write vapor pressure of the solution that is equal to PA plus PB, that is less than PA naught into xi A plus PB naught into xi B. Okay, these are the two conditions. Okay, that is the meaning of deviation. Vapor pressure of the solution is greater than that calculated by using Ross's law. Second condition is vapor pressure of the solution is smaller than that calculated by using Ross's law. Okay, that is the meaning of deviation. Based on these two conditions, we have two types of non-ideal solutions. Okay, yes, we can write that condition as first condition, vapor pressure of the solution is higher than that calculated from Ross's law. The first condition, vapor pressure of the solution is higher than that calculated from Ross's law. Second condition is vapor pressure of the solution is smaller than that calculated from Ross's law. Yeah. These are the two conditions. That is the meaning of deviation from Ross's law. In first condition, vapor pressure of the solution is higher than that calculated from Ross's law. Okay. Second condition is vapor pressure of the solution is smaller than that calculated from Ross's law. Okay. On the basis of these two conditions, we are classifying the non-ideal solutions into two types. Okay. First one is non-ideal solution showing positive deviation. Second type is non-ideal solution showing negative deviation from Ross's law. Okay. So in this case, if solutions obey this condition, that is the first condition, then that type of non-ideal solutions are called a non-ideal solution showing positive deviation from Ross's law. If the solutions obey these conditions, then that type of solutions are called non-ideal solutions showing negative deviation from Ross law. These two types and details, it is better to understand the relation between vapor pressure of the solution with the intermolecular force of attraction. Okay, if you take any liquid, then there is a relation between vapor pressure of that liquid with the intermolecular forces of attraction between the molecules of that particular component. Okay, so then we can write one relation: vapor pressure of the liquid is inversely proportional to intermolecular forces of attractions between the molecules of that particular liquid. Okay, it is at constant temperature. At constant temperature, we can write one simple relation: vapor pressure is inversely proportional to intermolecular forces of attraction between the molecules of the liquid. Okay, so clearly shows if intermolecular forces of attraction between the molecules of the component is very strong, then vapor pressure is low. And if intermolecular forces of attraction between the molecules of the component is weak, then that liquid has high vapor pressure. Okay, so clear, we can write if intermolecular force of attraction is strong, then vapor pressure is low. Vapor pressure of this solution is very low. Then if intermolecular force of attraction is weak, then high vapor pressure. Okay, that is the relation between intermolecular force of attraction and vapor pressure of the liquid. Okay, so take two liquids, that is A and B. Then just assume this one is A. Assume between A and A we have weak intermolecular forces of attraction, and take one more liquid, that is B. Between molecules of B we have strong intermolecular force of attraction. Okay, that's one molecules of A, B. Okay, just in liquid phase, vapor phase, liquid phase, vapor phase. Then according to definition of vapor pressure, what is vapor pressure? That is pressure exerted by the vapors of a liquid, right? Then in order to exert pressure, okay, this liquid molecules present in liquid phase, they should escape to vapor phase. If there is no vapor, that means that is non-volatile, then there is no concept of vapor pressure. In order to exert pressure, molecules of liquid, they should escape to vapor phase. That tendency of escaping, that is escaping tendency, is totally depends on the intermolecular forces of attractions between the molecules. If intermolecular forces of attractions are weak, then escaping tendency is more. Escaping tendency is more. Okay, if intermolecular force of attraction between molecules very strong, okay, in order to overcome the force of attraction, okay, it's very difficult, where less number of molecules will escape to vapor phase. Okay, so escaping tendency is here less. Escaping tendency is less. Escaping tendency is less. Okay, then clearly shows if intermolecular force of attraction is weak, is escaping tendency, that is molecules of present in liquid phase, they will easily escape to vapor phase. If intermolecular force of attraction between the molecules is very strong, then molecules of that liquid, they will escape to escaping tendency is very less. Okay, then here we can write more number of molecules of A that they will escape to vapor phase. In this case, very less number of molecules of B will escape to vapor phase. If more number of molecules are present in vapor phase, then vapor pressure is more. If less number of molecules are present in vapor phase, then its vapor pressure is low. This is the equilibrium condition. Okay, at equilibrium we are discussing this one. Okay, at equilibrium, if a system contains more number of molecules in vapor phase, then its vapor pressure is more. Then at equilibrium, if a liquid contains a less number of vapors, okay, then less number of molecules in its vapor phase, then its vapor pressure is very low. Okay, yes. So clearly it shows intermolecular force of attraction. It is the one deciding factor. Okay, in case of vapor pressure of types of non-ideal solutions. Okay, first one is non-ideal solution showing positive deviation, from Ross law. Positive deviation from Ross law. Non-ideal solution showing positive deviation from Ross law. Now what is the meaning of positive deviation? That is nothing but vapor pressure of the solution is higher than that calculated from Ross law, right? So we can write characteristic. First one is vapor pressure of the solution is higher than that calculated from Ross law. Okay. Then that type of non-ideal solutions are called non-ideal solution showing positive deviation from Ross law. You can take example of mixture of ethyl alcohol and acetone. Next we can take ethyl alcohol and cyclohexane. Okay, solution showing positive deviation from Ross law. Okay, then we can consider a solution, okay, of two components A and B. Okay, both A and B are volatile. Then between A and A, B and B, this one is before mixing. Okay, before mixing, okay, we have strong intermolecular force of attractions. Just assume, okay, in case of solutions showing positive deviation from non-ideal solutions, the components before mixing, they have very strong intermolecular forces of attraction. Then once if you mix, that is after mixing, okay, that process involves, that is mixing process involves breakage of strong intermolecular forces of attraction between molecules of pure components. Suppose in between A and A we have very strong hydrogen bonding. Between B and B, dipole-dipole interaction is there. That is two strong van der Waals forces of attractions between the molecules of the component. Then once if you mix A with the B, hydrogen bonding between molecules of A, that will break because of some of the molecules of B, they will interfere with the molecules of A. Okay, so a new interaction is established due to breakage of forces of attraction in case of pure components. This one is weak intermolecular forces of attraction. Okay, this in case of non-ideal solution showing positive deviation from Ross law. Initially in the pure state, that is a component in the pure state, they have strong intermolecular forces of attraction. Then once if you mix that one, that strong intermolecular force of attraction will break. They will form a new forces of attraction, that is weak. Okay, so if strong forces of attraction is there, then they are less volatile. So vapor pressure is normally low. That is a theoretical calculation by using Ross law. Okay, according to Ross, okay, they have very strong intermolecular force of attraction. So they are less volatile. That means escaping tendency of the molecules of pure component A and B is less. So their vapor pressure is normally low. Okay, that is neglecting the concept of intermolecular forces of attraction before mixing and after mixing. But here the fact, once if you mix these two components, okay, then magnitude of intermolecular forces of attraction decreases. Okay, we can say this one particular limitation of this Ross law. Okay, because according to Ross, there is no change in the intermolecular force of attraction before mixing and after mixing. But in case of non-ideal solutions, that is not true. Okay, before mixing and after mixing, there will be change in the intermolecular forces of attraction between the components. Okay, so here weak intermolecular force of attraction, so that is escaping tendency increases. Escaping tendency of molecule increases. Of molecules increases. So vapor pressure of the solution is higher than that calculated by using Ross law. Okay, yes, remember that point. In case of solutions showing positive deviation from Ross law, initially in the pure component, that is in the state of pure components, that is AA and BB, that is before mixing, they have strong intermolecular force of attraction. Once if you mix molecules of A and the molecules of A, they will interfere with the intermolecular forces of attraction of B. Similarly, molecules of B, they will interfere with the intermolecular force of attraction of A. Okay, due to that interference, okay, so there will be cleavage of a strong intermolecular force of attraction between the pure molecules of the pure components, and a new intermolecular force of attraction is established, that is weaker than the initial one. Okay, so if clearly it shows if the intermolecular force of attraction decreases, right, in this case intermolecular forces of attraction decreases. If intermolecular force of attraction decreases, we already discussed one relation, right, between vapor pressure and intermolecular force of attraction. If intermolecular forces of attraction decreases, vapor pressure increases. Okay, so this is the main reason for the positive deviation from Ross law, due to decrease in the intermolecular forces of attraction between the molecules due to mixing. Okay, yes, just take this one is A now. We have strong intermolecular force of attraction. Then you are mixing that with the B. Okay. This one is molecules of B. Then that will form solution A. That will form solution A. Okay. Upper one is now vapor phase, lower one is liquid phase. Okay. This one is vapor phase, this one is liquid phase. Here also vapor phase, liquid phase, vapor phase, liquid phase. Okay. Then in this case A, initially, that is in the pure state, we have strong intermolecular forces of attraction. Okay, strong intermolecular forces of attraction. So only few molecules of A, they will escape to vapor phase. Okay, in case of B also, strong intermolecular force of attraction, very few molecules of B that will escape to vapor phase. Once if you mix, okay, that will form AB-AB, right? AB-AB interaction is established. Okay. Remember, In this case, AB is not new type of molecule. This is not new molecule. Okay, this is simply attraction between molecules of A with the molecules of B. Then in this case, vaporization means what? This one is volatile means what? AB molecules together will not vaporize. They will not escape to vapor phase. Okay, A and B separately they will escape to vapor phase. Okay, so here force of attractions between A and B is very weak. So compared to initial case between A and B, very weak. Initially here A and A strong, B and B strong. It's very difficult to break these interactions. But in this case, AB interaction is very weak. Okay, more number of A and B, they will escape to vapor phase. Okay, more number of A and B, they will escape to vapor phase. Okay, clear? Because AB interaction is very weak, they will overcome that force of attractions very easily. Okay, so more number of A and B molecules, they will separately escape to vapor phase. So observe now initial case and final cases. This is in case of Ross law. Okay, in case of Ross law. Okay, because intermolecular force of attraction before mixing and after mixing is same. Okay, only we have 1, 2, 3, 4, 5, somewhat very less number of molecules in the vapor phase. But practically it is observed that okay, after mixing, force of attraction between the component molecules of the component decreases. So more number of molecules will escape to vapor phase. So vapor pressure is high. Okay, compared to the Ross law. Okay, so vapor pressure of the solution that is equal to PA plus PB. This one vapor pressure of the partial vapor pressure of component A, partial pressure of component B, that is greater than that calculated by using Ross, law. Okay, that is in case of a non-ideal solution. Yeah, vapor pressure of the solution that is equal to PA plus PB. Okay, PA plus PB, that is greater than that calculated by using Ross law, because according to Ross law there is no change in the intermolecular, that is in Ross law is nothing but in case of ideal condition there is no change in the intermolecular forces of attraction before mixing and after mixing. But in case of non-ideal condition, in case of positive deviation, after mixing, intermolecular forces of attraction between the molecules of the component decreases. So more and more molecules will escape to vapor phase. So vapor pressure of the solution is higher than that calculated by using Ross law. Okay. Second characteristic, that is heat change. Okay. In case of non-ideal solution showing positive deviation, heat change on mixing is equal to positive. For ideal solutions, heat change on mixing is equal to 0. In case of non-ideal solutions, we are writing heat change on mixing is not equal to 0, right? Then in case of non-ideal solution showing positive deviation, here heat change on mixing is equal to positive. Okay, so heat change on mixing is positive. Heat change on mixing is positive, that is delta H. Heat change on mixing is positive. Heat change on mixing is positive. Okay, so consider a volatile solution of two liquids A and B. Okay, then between A and A we have strong intermolecular force of attraction. Between B and B also we have strong intermolecular forces of attraction. Once if you mix, that will form AB, that is a solution. Then intermolecular forces of attraction between this one is weak. So that is the first characteristic of non-ideal solution showing positive deviation, right? Clearly it shows. So magnitude of strong, weak, right? Before mixing, strong intermolecular force of attraction. After mixing, weak intermolecular force of attraction. Okay, so magnitude of intermolecular force of attraction decreases. Magnitude of intermolecular force of attraction decreases, right? So in that case, delta H mixing is equal to positive. Remember, if in a solution of two components, while mixing, if magnitude of intermolecular force of attraction decreases, then delta H is positive. Okay, we'll discuss why. We'll taking example of ethanol and acetone. Ethanol and acetone. Okay. Now, between ethanol molecules, ethanol and ethanol, okay, we have hydrogen bonding. We have, right, what is while writing two molecules of ethanol, we can join them by using hydrogen bonding, because ethanol molecule contains more electronegative oxygen atom along with that electropositive hydrogen atom, right? So they will form hydrogen bonding. Okay, hydrogen bonding is a strong intermolecular force of attraction between any two molecules. Then if you take acetone, okay, between acetone molecules we have dipole-dipole interactions. Dipole-dipole interactions, okay, dipole-dipole interaction. This one also strong intermolecular forces of attraction between any two molecules. Okay, so clearly shows ethanol and acetone is the before mixing. Okay, before mixing we have strong intermolecular forces of attraction. Then once if you mix these two components, acetone molecules, they will interfere with the force of attraction between ethanol molecules. So some of the acetone molecules will enter into the empty space of ethanol molecules. That leads to the breakage of this hydrogen bonding. Clear? Acetone molecules, they will enter into the between ethanol molecules. So that leads to the breakage of hydrogen bonding of ethanol molecules. So then between ethanol and acetone, a new force of attraction is established. Okay, this one is weak compared to this hydrogen bonding. Okay, that is compared to this hydrogen, because ethanol and acetone, they can also form hydrogen bonding. Okay, but this hydrogen bonding somewhat weaker than this hydrogen bonding in case of pure ethanol molecules. Okay, so clearly this process involves breakage of hydrogen bonding. So always bond breaking is an endothermic reaction, right? Process, right? Bond breaking is always endothermic. In thermodynamics, for endothermic process we are writing delta H, that's enthalpy changes positive, right? So delta H mixing is positive. This process, in case of non-ideal solutions showing positive deviation, the mixing of two component process involves breakage of strong intermolecular forces of attraction between the pure molecules. That is pure components. Again, the pure components, we have strong intermolecular forces of attraction. If you mix that two pure components, that process involves breakage of strong intermolecular forces of attractions between the molecules. So because of that reason, for non-ideal solutions showing positive deviation, enthalpy change on mixing is always equal to positive. Okay, so remember this point. But bond breakage, along with that, there is some bond formation also takes place, right? That is bond new force of attraction takes place, but this one is weak compared to initial one. Okay, remember that point. Magnitude of intermolecular force of attraction decreases. Initial magnitude of initial forces of attraction between the pure component is stronger than the final one. Okay, for that reason magnitude of intermolecular force of In this case, ethanol and acetone mixing process involves breakage of hydrogen bonding between ethanol molecules. Clearly, bond breakage is always endothermic process. That means we require some amount of energy in order to break the bond. So, energy is absorbed during that process. During that process means during dissolution process, energy is absorbed. So, that is endothermic process. Okay. So, in case of non-ideal solution writing, showing positive deviation from roster, we can write dissolution process is endothermic. Okay, so we can write dissolution process is endothermic. Dissolution is processes endothermic. That means if you increase temperature, the solubility increases. Okay, third characteristic, that is volume change. Okay, volume change or mixing. In case of ideal solutions, volume change on mixing is equal to 0. In case of non-ideal solutions, we are writing volume change on mixing is not equal to 0. In case of non-ideal solution showing positive deviation from roster, volume change on mixing is equal to is positive. Volume change on mixing is positive. That means take two components A, you are mixing that with B. You are taking 10 ml of A, 10 ml of B. In case of ideal solution, what is the final value of volume of solution? That is 20, right? But in case of non-ideal solutions, showing positive deviation, okay, 10 ml of A with 10 ml of B, that will form solution AB. Okay, in case of that one, volume is greater than 20 ml. Greater than 20 ml. Just assume that is somewhat 21 ml. Then volume change delta V mix is equal to V final minus V initial, that is equal to 21 minus 20, that is equal to 1 ml, nothing but that is delta V mix is equal to positive. Clear? That is the meaning of the volume change on mixing is positive. Okay. In case of non-ideal solution showing positive deviation, if you mix two components, final volume is higher than the initial volume. Okay. So we'll discuss what is the reason for this volume change on mixing is positive. As you know, in case of non-ideal solution showing positive deviation, before mixing, the pure components will have very strong intermolecular force of attraction. If the intermolecular force of attraction between the components is very strong, then they are tightly bound to each other, right? Molecules are tightly bound to each other. Clear? That is in case of pure components. Intermolecular force of attraction is very strong. They are tightly bound to each other. Okay, so they will occupy less volume. Then once if you mix that one, in case of first characteristic we already discussed, if you mix these two pure components, in case of non-ideal solution showing positive deviation, magnitude of intermolecular force of attraction between the component decreases. If magnitude of intermolecular force of attraction decreases, then they are loosely bound to each other. Molecules, okay, loosely bound to each other. If they are molecules are loosely bound to each other, then volume occupied by the molecules increases. Clearly we can observe this is in case due to weak intermolecular forces of attraction between the molecules. Okay, they are loosely bound to each other. If they are loosely bound to each other, volume obviously increases. Okay, that is a simple explanation. Okay, if you mix ethanol with acetone, okay, final volume of the solution is higher than the initial volume of the pure components, because if you mix that one, intermolecular forces of attraction between the molecules decreases, so molecules will loosely bound to each other. Because of that reason, their volume increases. Okay, yes, in this case, strong intermolecular forces of attraction molecules will tightly bound to each other. Clear? Once if you mix, intermolecular forces of attraction between the molecules of the component decreases, so they are loosely bound to each other, so their volume increases. Next topic, that is graphical representation of non-ideal solution showing positive deviation. Okay, just consider a solution of two components A and B. Consider a solution of two components A and B. Okay, let xi A be the mole fraction of A, mole fraction of A, and xi B, let it be the mole fraction of B, mole fraction of B. Then let Pa naught, let it be the vapor pressure of pure component A, vapor pressure of pure component A. Then let Pb naught be the vapor pressure of pure component B, pure component B. Okay, then okay, here take mole fraction of B along the x-axis, vapor pressure along the y-axis. Okay, at this point we have only xi A, so xi A equal to 1, xi B equal to 0. You know, right? If you take a solution, sum of the mole fraction of any components present in the solution is equal to unity. So here we have two components. Xi equal to 1 means obviously xi B equal to 0. Then mole fraction of A decreases along the x-axis. Here we reach xi A equal to 0 at this point. There we have xi B equal to 1. Then according to Ross law, Pa, partial vapor pressure of A, is directly proportional to xi A, right? So you can observe here xi A equal to 1, that means we have only A, so vapor pressure corresponding to that point is nothing but Pa naught. Okay, Pa naught. Then along the x-axis, vapor pressure of or mole fraction of A decreases. According to Ross law, if mole fraction of A decreases, vapor pressure also decreases. So we can write, so along the x-axis, mole fraction of A decreases, so vapor pressure of the solution also decreases. Then assume this, out of two components, B is more volatile. Okay, B is more volatile. B is more volatile. Any one of the component is more volatile. I am assuming here B is more volatile. Then take component B. Okay, component B. Here 0. So according to Ross, Pb is directly proportional to xi B. So xi B equal to 0 means 0. Then mole fraction of B increases along the x-axis. If mole fraction of B increases, vapor pressure also increases. So this point we have only B, that is nothing but pure component B. Vapor pressure corresponding to that point is Pb naught. Okay, then if you join these two lines or points, that is Pa naught and Pb naught, that will give vapor pressure of the solution P total equal to Pa plus Pb. That is according to Ross law. So that is the graphical representation of ideal solutions. In case of non-ideal solution showing positive deviation, vapor pressure of A, okay, that is greater than that calculated by using Ross law. This dotted line indicates the vapor pressure calculated by using Ross law, but actually experimentally it is observed that vapor pressure of the solution is greater than that calculated from Ross law. Okay, you can observe positive deviation, right? Vapor pressure of the solution is greater than that. Here vapor pressure of A, that is greater than Here you can observe vapor pressure of A is greater than that calculated from Ross law. For B also, vapor pressure of B that is greater than that calculated by using Ross law. Dotted line indicates the vapor pressure that is of B that is calculated by using Ross law. This solid line indicates the vapor pressure of the B that is experimentally calculated value. Clearly you can observe experimentally calculated value is more than that the calculated by using Ross law. Okay. Then total vapor pressure of the solution P total that is also like this. Okay. This dotted line joining PA naught and PB indicates the vapor pressure of the solution that is calculated by using Ross law. Experimentally observed values this one. You can observe vapor pressure of the solution is more higher than that calculated from Ross law. Right? This one is now vapor pressure of solution. Okay. Experimentally calculated value. That vapor pressure of the solution is higher than that calculated from Ross law. Okay. This is the graphical representation of non-ideal solution showing a positive deviation. So now clear it what is the meaning of positive deviation. Vapor, we can observe each line vapor pressure of the components and solution is higher than that calculated from Ross law. Okay. Except is next topic, non-ideal solution showing negative deviation from Ross law. You know, negative deviation means the vapor pressure of the solution is lower than that calculated from Ross law. Okay. Then we can write expression as P total, that is vapor pressure of the solution, is equal to PA plus PB, that is lower than that of PA naught into Xi A plus PB naught into Xi B. Right? Vapor pressure of the solution is lower than that calculated from Ross law. Okay. Yes. Consider a solution that is made up of two components. Okay. A then B. Okay. A and B. In this case, they have weak intermolecular process of attraction. The components in the pure state have weak intermolecular process of attraction. Once if you mix that one, that will form solution. In solution, they have strong intermolecular process of attraction. So we can write magnitude of intermolecular process of attraction increases. Magnitude of intermolecular process of attraction increases. So if the intermolecular process of attraction between the component is weak, then escaping tendency is more. Escaping tendency is more. So high vapor pressure. That is theoretically we are assuming like that, right? In pure component, if you take, they have weak intermolecular process of attraction. That means more number of molecules will escape to vapor phase. So its vapor pressure is high. But once if you mix the two components, magnitude of intermolecular process of attraction increases. So escaping tendency decreases. Escaping tendency decreases. Escaping tendency decreases. They have low vapor pressure. That is what happens in case of non-ideal solution showing negative deviation. Okay, initially they have weak intermolecular process of attraction between the molecules, but once if you mix that two components, their intermolecular process of attraction increases. If the intermolecular process of attraction between the molecule increases, their escaping tendency decreases. Okay, so vapor pressure also decreases. Take this one in case of between AA in liquid phase. Okay. This one is B. Okay, we have weak intermolecular force of attraction. Here also weak intermolecular force of attraction between the molecules. Okay, then if intermolecular force of attraction is weak, more molecules will escape to vapor phase. More number of molecules will escape to vapor phase. As the number of molecules in the vapor phase increases, vapor pressure also increases. But if you mix these two, that will lead to formation of solution AB. Okay. In case of AB, we have strong intermolecular forces of attraction. Okay. AB, we have very strong intermolecular force of attraction. That means in order to overcome into strong intermolecular force of attraction, it's very difficult. Okay, so escaping tendency decreases here. If escaping tendency decreases, very few molecules will escape to vapor phase. This theoretically we are assuming like this. In the pure state, their vapor pressure is very high, because intermolecular force of attraction between the molecules is very weak. But once if you mix that one, intermolecular forces of attraction between the molecules increases. Okay, so escaping tendency decreases. So number of molecules present in the vapor phase decreases. So vapor pressure of the solution decreases. So there is a meaning of magnitude of intermolecular forces of attraction increases. Okay, if magnitude of intermolecular forces of attraction decreases upon mixing, then vapor pressure of the solution is lower than that calculated from Ross law. Okay, that is the reason for the negative deviation from Ross law. Okay, yes, is the first characteristic. The characteristic is heat change on mixing is negative. For ideal solution, that is equal to 0. For non-ideal solution showing positive deviation, that is positive. For non-ideal solution showing negative deviation, heat change on mixing is negative. Okay, so remember one point, as magnitude of intermolecular force of attraction increases, then delta H mix equal to negative. Okay, so between A and B we have weak intermolecular forces of attraction. Once if you mix that one, that will form solution AB. We have strong intermolecular force of attraction. Clearly can observe initially weak intermolecular force of attraction. Once if you mix, there will be formation of it. So there will be establishment of a very strong intermolecular force of attraction takes place. So in that case, delta H mix equal to positive. Okay, remember one point. If in the solution phase, upon mixing two components, if magnitude of intermolecular forces of attraction increases, then that dissolution process is exothermic. That means delta H mix is equal to negative. You can write dissolution process is exothermic. Okay, upon mixing two components, if magnitude of intermolecular forces of attraction between the component increases, then that dissolution process is exothermic. We can take example of acetone and chloroform. Okay, this one's example for non-ideal solution showing negative deviation. Okay, then if you take acetone, between acetone and chloroform, okay, we have weak intermolecular forces of attraction. Then if you mix that one, okay, there will be hydrogen bonding between acetone and chloroform. Okay, there will be formation of hydrogen bonding between acetone and chloroform. What is acetone? that hydrogen bonding is very strong intermolecular forces of attraction between molecules, right? Now take acetone is CH3, C double bond O, CH3, chloroform is Cl3, CH. Between hydrogen atom of this chloroform and oxygen atom of this acetone, there will be formation of a hydrogen bonding takes place, okay? Hydrogen bonding takes place. So clearly you can observe initially acetone we have dipole interaction. After that between acetone and chloroform molecule there will be formation of hydrogen bonding takes place. So clearly magnitude of intermolecular forces of attraction increases or there will be formation of a bond takes place, right? So you know bond formation is always exothermic reaction, exothermic process, okay? Bond formation is exothermic, okay? In this case there will be formation of hydrogen bond between acetone and chloroform molecule. So if you mix acetone with chloroform, that dissolution process is exothermic, heat is released during that process, okay? Because due to increase in the magnitude of intermolecular forces of attraction, okay? So you can write delta H mix equal to positive. So remember that point. If magnitude of intermolecular force of attraction decreases, then delta H mix is positive. Then dissolution process endothermic. If magnitude of intermolecular force of attraction increases upon mixing, then delta H mix is negative, okay? So if delta H is positive, then that dissolution process is endothermic. If delta H is negative, then that dissolution process is exothermic, okay? Next point, there is volume change on mixing is negative. In case of non-ideal solution showing negative deviation, volume change on mixing is negative. So take two components A and B. You are taking 10 ml of A, 10 ml of B. Upon mixing that will form a solution. Then in solution volume is always less than 20 ml. Just assume that is somewhat 19 ml you are getting. So we can calculate delta V, volume change on mixing, equal to V final minus V initial, that is equal to 19 minus 20, that is equal to minus 1. Okay, minus 1 means what? There is no value for minus volume like minus 1 volume. Okay, minus 1 indicates volume is decreased by 1 unit, okay? Yes, so you can observe in case of non-ideal solution showing negative deviation, if you mix that to pure components, volume of the solution is always smaller than the volume of the pure components, okay? So that is because in case of A and A, we have very weak intermolecular force of attraction. So if intermolecular force of attraction is weak, then molecules are loosely bound to each other, okay? This one is between B and B, very weak intermolecular force of attraction. If intermolecular force of attraction between the molecule is weak, then the molecules are loosely bound to each other, so obviously they will occupy large volume. Then upon mixing these two components, intermolecular force of attraction increases. Magnitude of intermolecular forces of attraction between the molecules of the component increases. If magnitude of intermolecular forces of attraction increases, okay, then their molecules of the components are tightly bound to each other. A and A loosely bound to each other due to weak intermolecular force of attraction. A and molecules of A and B, okay, they are tightly bound to each other because of strong intermolecular forces of attraction. So obviously if molecules are tightly bound to each other, volume of the solution decreases, okay? They will occupy smaller volume than pure components, so obviously volume of the solution decreases, okay? So we are getting delta V mix is equal to negative. Delta V mix equal to negative. Next is graphical representation of non-ideal solution showing negative deviation, okay? Graphical representation of non-ideal solution showing negative deviation. So Consider a solution of two volatile liquids A and B. Let xi A be the mole fraction of A and xi B be the mole fraction of B. Okay. Then draw a graph of mole fraction of B versus vapor pressure. Okay. At this point we have only A. So vapor pressure corresponding that point is PA naught. Assume P component B is more volatile than A. Okay. Then according to Ross law, PA is directly proportional to xi A. At this point, mole fraction of A decreases. Then vapor pressure of A also decreases. Okay. Then mole fraction of B increases along the x-axis. So PB naught. Okay, this corresponding to B. We have only component B, so PB naught. If you join that 2 points, PA naught and PB, that will give vapor pressure of the solution. That is in case of ideal conditions. But in this case, we are taking non-ideal solution showing negative deviation. So vapor pressure of the solution is lower than that calculated from Ross law. This dotted line indicates the vapor pressure of the component A, okay, according to Ross law. This solid line indicates experimentally calculated vapor pressure of A, that is smaller than calculated from Ross law. Here also vapor pressure of B, okay, that is smaller than that calculated from, lower than that calculated from Ross law. Then vapor pressure of the solution also lower than that calculated from Ross law. Okay, this dotted line indicates vapor pressure of the solution calculated by using Ross law. This solid line indicates the vapor pressure of the solution, that is experimentally determined value of vapor pressure of the solution. Clearly we can say vapor pressure of the solution is lower than that calculated from Ross law. Okay. This next, that is differences between non-ideal solution showing positive deviation and non-ideal solution showing negative deviation. Okay, that is the overall summary of the two topics. Okay, yes, in case of non-ideal solution showing positive deviation, vapor pressure of the solution is higher than that calculated from Ross law. In case of non-ideal solution showing negative deviation, vapor pressure of the solution is lower than that calculated from Ross law. Okay. The second point, that is about the forces of attraction between forces of attraction before mixing and after mixing. Okay. Then in case of non-ideal solution showing positive deviation, forces of attraction between solid to solvent molecule will be less than that of solid and solvent to solvent molecules. Okay. Next, in case of non-ideal with negative deviation, forces of attraction between solid to solvent molecule will be more than that of solid to solute and solvent to solvent molecules. Remember that point. In case of positive deviation, magnitude of intermolecular forces of attraction decreases upon mixing. In case of negative deviation, magnitude of forces of attraction between the molecules increases upon mixing. Next, third point about heat change on mixing. In case of positive deviation, heat change on mixing is positive. That means dissolution process is endothermic. In case of non-ideal with a negative deviation, heat change on the mixing is negative. That means dissolution process is exothermic. Next, in case of positive deviation, volume change on mixing is positive. In case of negative deviation, volume change on mixing is negative. Okay.